Yeah, thank you for the invitation to speak at this workshop. So today I decided to talk about something very elementary. It's a little unfinished project of mine, which I decided to share even though it's not really finished. But the good news is precisely there. I mean, the reason it's not finished is because there are some questions which I can't answer. So apparently 4 years ago at IPAM, I asked some questions and they got answered in this meeting. So maybe in 4 years, I can come back here and people will, oh, maybe before that, because these questions are actually fairly elementary, contrary to the one that John solved. These are very simple combinatorics questions I can't answer. So hopefully somebody in the audience can answer them for me. And so the plan is extremely simple. As you can see, I don't have many slides either. So it's basically just about, this paper by Lascoux and Schutzenberger, who have been, oh yeah, I should also apologize to the experts, especially the previous speaker, that these things, some of you know all this story by heart, but I'll go through that anyway. So in particular, I'll go through this old paper of Lascoux and Schutzenberger. And they talk about, so it's a paper in French, as you can see from the title. So lattices and bases, I guess, of Coxeter groups. And this paper, I always found that was, there is a discussion there which I want to basically extend to type B. So there is, even in that paper, something about type B Coxeter, well, Weyl groups, but it's the discussion is not quite right. So we need to fix that discussion. And in the process, we'll have an explicit description of the MacNeille completion of type B Bruhat posets, which is the goal of this talk. So it's extremely simple, and I'll spend a lot of time just doing, basically just rephrasing, I could say translating into different language the paper of Lascoux. Pun intended, the original paper was in French, but it was purely combinatorial. And I think it's nice to throw in a bit of geometry as well too. A lot of the arguments become a lot nicer if you think about them a little bit more geometrically. And also if you think about the connection to, at some point I'll talk about the connection to lattice models, obviously, which is my field. So, and that's it. So first, yeah, very basic definitions. So this is literally just elementary algebraic combinatorics. So we're playing with posets. So you start with a poset, and by the way, all my posets are going to be finite. So a lot of these definitions, like for example, the notion of a lattice versus complete lattice, all these subtleties are irrelevant. All our lattices are going to be, all our posets are going to be finite. So P is a lattice, or more technically, a complete lattice, if every subset admits a least upper bound, like a subprimum, right? And incidentally, if you've never thought about this, probably you have, but if every subset admits a subprimum, then it also admits an infimum. So there's no, it's completely symmetric. So, but you might as well just give one of the two properties. So that's what we. So the basic, objects in this story are just basically just posets and lattices, and when are posets lattices and when they're not. So if they're not, then you might hope to somehow complete your poset into a lattice. And so that's the notion of a MacNeille completion. That's the, this is the whole story here is simply we want to construct for a given poset its MacNeille completion. And so there's a formal kind of definition, like abstract nonsense type universal property for MacNeille completion. It's the smallest lattice which contains P as a subposet. So you have this category of lattices with order embeddings from a given poset to that lattice, and you want to find some initial object or whatever. But the good news is you don't need this abstract nonsense. You can construct it completely explicitly. And in other words, not only is there a construction, which it better be if you want your universal property to have a solution, but it has a very canonical solution in some sense. And the way you construct the MacNeille completion is very simple. It's going to live inside the power set of P, so which I denoted 2 to the power P, which is itself a poset under inclusion, but actually, there are choices to be made, conventional choices. It's more convenient to think about reverse inclusion as your partial order. And so the way it works is, the intuitive idea is very simple. You're going to encode every element of P as a subset of P, which is exactly, I always forget in poset theory what it's called, the set of all elements that's greater or equal to that given element.
Order ideal.
It's not an order ideal, is it?
Upset.
Thank you. That's the one. And then you're going to say, well, okay, there's another condition which is always, we don't need actually in all over. You also need to have P as a subset of P living in there, which is, we don't need it because we always have well, we have both greatest and smallest elements in all our posets. So that condition is not so important, but the most important one is the third one. Once you have those, you basically start intersecting them. So you want it's the smallest subposet which is stable by intersection. So again, since all our posets are finite, really all it means is you start with these particular subsets, you start intersecting them until you're done. Basically, you have a collection of all the possible intersections. That's your MacNeille completion. And incidentally, yeah, so I already said P embeds into P tilde as we just discussed, and also in this language, the subprimum is nothing but the intersection. And again, remember, my inclusions are inverted, so intersection creates a bigger element, not a smaller element.
Oh, I'm confused, and I just feel myself being about to say something really stupid here, so I'm going to.
Oh, it's perfect. This talk is all about, yeah.
Okay, there's that. Can I not just add a maximal element? No, every element is every subset of P has a sup. It's that or lower. But that's not your MacNeille completion. That's something boring. So what am I missing?
You know, we're going to very quickly go through the same example that was already in the previous talk, which is the case of S3. Then you'll see exactly what can go wrong, like even inside the poset. So in other words, the point is every subset has to admit a supremum, right? So you might
other relations somehow, other than just existence of supreme, some lattice.
Uniqueness.
No. I mean, if you're going to add new elements, then you have to make sure that the new elements that you add also talk well to the existing elements, right? You can't just willy-nilly add.
Hopefully it'll become clear on
okay, I'm sure it'll become clear.
Yeah. Okay, so next thing I want to talk about is, so I want to define Bruhat order. And again, you can define it purely combinatorially as in the paper of Lascoux and Schutzenberger, but I'd rather think about, basically secretly like Schubert varieties or related objects. So it's going to be very closely connected to the previous talk, but I'm going to use a slight variation, which is matrix Schubert varieties, just because they're a little bit easier to think about. So first we start with a reductive algebraic group, G, and then so I'll use both Borel subgroups for, this is not so important, you could use only one of them. So think of G, so in the whole first part of the talk, G will be GLN, B plus minus will be upper and lower triangular invertible matrices, and T is the Combinatorics, is just the invertible diagonal matrices, and finally W is the Weyl group, which in type A is just the symmetric group. For me, type A, GLN is type A. I'm not going to distinguish GLN versus SLN. It's not so important for today. And so, yeah, so the most important result is that there is this Bruhat decomposition. So in other words, I let B minus act on the left on G and B plus act on the right, and then you have this nice decomposition, G as a disjoint union of orbits where the representative elements, you can think of them as Weyl group elements, right? So think generalized LU decomposition. Almost every matrix can be written as lower times upper, except sometimes it doesn't quite work, so you have to stick in a permutation in the middle. And that's what I just said, yes. And in this picture, if you in the type A, W, when I said W is the permutation group, you can actually identify it non-canonically with just permutation matrices. So matrices with exactly 1, 1 on each row and column. All right. And so how do you define the Bruhat order in this kind of geometric manner? It's very simple. It's kind of a completely general construction. Whenever you have such anyway, you just take the closure of all these orbits, and you say that, so again, you have to be careful with so it's again, reverse inclusion on these XWs give you the Bruhat order. So W less than W prime if XW contains XW prime. So of course you can describe more explicitly, what that order is, but we don't need to. So let's go through an example, which is the example of GL3 and S3. So in all these cases, you can really write explicitly what all these X's are, right? So they're subsets of, GL3, so invertible matrices, and they have to satisfy, because they're in some orbit of some, do I have a pointer? Yeah, of some permutation matrix, they have to satisfy certain properties. For example, the simplest one is if you look at the orbit of the 3-to-1 permutation matrix, you'll find that it always has zeros in this upper left corner, and so these zeros can go away even if you sweep with B minus cross B plus, so they're going to stay there, and that's it. That's the description of the whole orbit. So invertible matrices which had zeros there. In fact, all of these XW in the case of S3 are basically sets of matrices where you have some zeros somewhere, and there's only one exception, which is 1, 3, 2, which has a, which is a bit more complicated, and we'll get back to that eventually. It satisfies some rank condition. The top left 2 by 2 matrix has to be of rank less or equal to 1. So it has, explicitly, that means there's some minor that's equal to 0. And finally, always the biggest element is just the space of all matrices, because as I said, almost every matrix can be written as lower times upper. Okay, and so now these are the different pieces of the puzzle, but then the arrows are the covering moves of the Bruhat order, and so they just reverse inclusion. So this contains everything, and so on. And so in particular, you see you have this interesting crossing in the middle. So I mean, you could have, of course, drawn this picture in a different way. You could have swapped these two, but you'd still get all of these arrows going from this row of the diagram to this row. And in particular, no matter how you draw this poset, you'll have a kind of a crossing in the middle, which is a sign that something's going wrong. And so the way you can see more explicitly something is going wrong is you ask for the question, what is the, so now here's maybe an answer to your question. Here's a nice counterexample. You take the supremum of 2, 1, 3 and 1, 3, 2. And you see that means you're supposed to consider all the things that are above, and you're supposed to find the smallest element. And there is no smallest element there, because you have these two are incomparable. So yes, so it has to be a least, that's right. Okay, now I understand your question. Yes, the least element has to be the, well, yes. It has to be smaller than everyone, therefore, by definition, it has to be unique. Yes, that's right. So in this case, you're stuck, so there's no such supremum, so it's not a lattice. Okay. Now, how do you solve the problem? So the good news is, again, completely tautologically, there is an answer to how to define the MacNeille completion in the case of Bruhat posets. And the reason is that, effectively, the Bruhat decomposition is really telling you that there is an order-preserving bijection between B minus cross B plus invariant subsets of G and the power set of W, right? And it sends XW to, well, the well, if you think of XW as kind of like, so remember XW is the closure, so naturally, when you take the closure, you pick up everything that's, well, smaller in containment and therefore greater in reverse containment, so that means you pick up exactly all the elements of W that are greater or equal to W. So in other words, we've really realized using this Bruhat decomposition exactly that kind of canonical construction of the MacNeille completion, right? So more explicitly, maybe this is a bit of a mouthful, so the translation into more concrete language is that the small set of B minus cross B plus invariant subsets of G containing the XW unstable by intersection is exactly the MacNeille completion of the Bruhat posets. So even more explicitly, that means you start with those XWs, you intersect them as many times as you can until you've exhausted all the possibilities. That's your Bruhat poset. So let's do it in our example. So we found out that there was really only one problem with this picture, which was these, these two didn't have a supremum, so we're going to try to apply this little game of intersecting to these two varieties. So we're going to take the intersection of x213 and x132. And so I even gave you the completely explicit equations here. Sorry, I'm getting a little confused with why I can't get that thing to reappear. It was there. You can even see it. It is very confusing. Here we go. So you're supposed to intersect, this is like elementary algebra. You have m11 equals 0. You have m11, m22 minus m12, m21 equals 0. You impose both equations. You get this m12, m21 equals 0. You have to make a choice. Either this is 0 or this is 0. So you get two pieces, two irreducible components, if you like. So either m120 and m21 equals 0. And then you recognize this is nothing but the union of the top two, the things on the row above. So the intersection of these two is the union of these two. And by the way, you're not allowed to do arbitrary unions. It is always true, of course, that any intersection will be some finite union of the XWs, but you don't get every union this way. But in this case, you get exactly the union of these two. So the picture now looks like this. This is your type A GL3 poset. So there's one extra element, which is these. Either you can think of the intersection of these two or the union of these two. And of course, now you see there are 7 of them. And 7, we saw in the previous talk, is the number of alternating sign matrices. So that's no coincidence. So we're going to go through that now. OK, so now we're going to do the the discussion of type A, which is, as I said, already in this old paper of 1996. And sorry, I just want to see. Yeah, clock here. All good. OK, so type A. So the first thing I'm going to do is, so I'm going to work now for general n, g equals gln. And the first thing I'm going to do is I'm going to ignore the distinction between gln and all matrices of size n. In the whole discussion that I had before, all the matrices were supposed to be invertible, but that actually plays absolutely zero role. So for all practical purposes, you can redefine x, sorry, that's a typo, xw to be the closure not in gln, but in the whole of the n by n matrix set of n complex matrices of the same b plus w b minus. So that subtle redefinition is exactly at the heart of what's called, matrix Schubert variety. So that is a matrix Schubert variety, and for all practical purposes, it has the same properties as the thing in gln, which would be closer to ordinary Schubert varieties. And it's the same thing that goes from those, abstract Schubert classes in G mod B to actual polynomials like Schubert polynomials. We're not going to talk about Schubert polynomials in this talk. I'm just mentioning this as kind of connecting to the previous talk. But anyway, so you can safely ignore this distinction. Don't worry about it. It's really not so important. It just makes things slightly easier. I don't have to repeat each time, oh, and these matrices have to be invertible all the time. OK, so now comes the general description. This is well known. This is, I don't know who wrote this first, but you can write explicitly the equations defining SW as a, as a algebraic subvariety, if you want, of n by n matrices. They always rank conditions involving submatrices, northwest submatrices of the matrix. So we saw some examples. So maybe I should go back to the example. There we go. So you can think of all these zeros here as secretly telling you that, like this northwest 1 by 1 submatrix is 0, or actually this 1 by 2 northwest submatrix is of rank 0 and therefore 0, or this one, or this one. So all these conditions are secretly rank conditions on the northwest submatrices, and the only non-trivial example being this one. And as I already pointed out, this only is just a way of writing the fact that this 2 by 2 submatrix is of rank at most 1. And so this is a general fact. You can always write this as a rank submatrix. And in fact, the rank, we know what it is, because in particular, in each of these XWs, there is the permutation matrix itself. So all you have to do is compute the rank for the corresponding permutation matrix, and that's very easy. Computing a rank of a permutation matrix, we learned that in first year linear algebra. So it's literally the sum of all the entries of W if you think of it as a matrix with zeros and ones. So you just pick any submatrix of W, compute the number of ones in there, that's your rank. OK, so we have a completely explicit description of these XWs. And now, so very naturally, we led to this rank matrix. So this is what I just said in words. If you want to compute the rank of a submatrix of size, northwest submatrix of size ij, all you have to do is basically sum up all of these entries. So you can turn that into a matrix of size, well, n plus 1 if you allow zeros, which is just these partial sums. And so that encodes entirely all these rank conditions for the matrix Schubert varieties. But you can see that these are ij's, so they're arrays of integers, but they satisfy inequalities, well, equalities and inequalities. So first, there are some obvious boundary conditions. I added an extra, allowed the possibility of these indices being 0, but that, of course, means the sum is 0. So R 0, R 0, J equals 0. Also, for trivial reasons that these are permutation matrices, at the other end, R I n or R and J have the value I. So you have some definite values on the boundaries of the square. And then you have an extra condition, which tells you that the rank of a matrix cannot change that much when you add a row or a column. And so that's exactly what these conditions are telling you here. So if you add one row, add one column, either the rank stays constant or it increases by 1. Easy. And so why do I care about these rank matrices? As I said, they encode entirely the geometry of these matrix Schubert varieties. That means they also encode entirely the Bruhat order, because the inclusion of a variety into another is exactly about saying that one of the rank conditions implies the other rank condition, which is just inequality on these Rij's. So another way of saying that is that the Bruhat order is nothing but entry-wise inequality of the corresponding rank matrices. And another good news is even the lattice structure is kind of obvious. Intersecting things is about taking the inf of the two possibility. So in other words, intersecting two varieties given by rank conditions is just about taking the inf of the rank at every point, which is, again, the obvious thing. So we've entirely encoded now the sort of combinatorics into those rank matrices. OK, at this stage, I could just stop there. That's actually, that's it. That's the whole analysis in some sense. For technical reasons, I actually prefer to use something I call the height matrix. This is like, we like that better in statistical mechanics. It's almost the same. One way you could justify is the fact that you prefer to work with subprimums rather than infimums. That's a kind of a really lame reason for doing that. But there are other reasons. I mean, it's more symmetric this way. So I'm going to do some slight redefinition. It's, of course, the exact same information. I'm going to define a new matrix, integer-valued matrix, which I denote H sub ij. And it's just I plus j minus 2 rij. And the reason I do that is just it looks a little bit more symmetric. So the boundary conditions become a little bit different, but whatever, they're what they are. So you still have fixed values of this height matrix when any of the two indices is either 0 or n. And now the condition that says that nearest neighbors had to be either 0 or 1, now it looks a little bit nicer. It's minus 1 and 1, and I like that symmetry. OK. But for the rest, nothing has really changed, right? So in particular, if you have a subvariety given by rank conditions given by Rij, well, you can go back and forth between the two, basically. And so in particular, now we're back to having, like, reverse inclusion is about now less or equal entry-wise. And the height of the intersection is more like the supremum of the heights. But so all I've changed is everywhere I've changed all the inequalities in the other directions. But it doesn't really make any big difference. So I will show you in a sec, again, the example n equals 3. But first, let me state the obvious theorem. And I will actually prove that theorem. That's one of the theorems of the paper of Lascoux and Schutzenberger. And in fact, I will give you their proof, just maybe slightly. I mean, in other words, nothing what I'm saying now is original. But so here's one of the simple propositions that they have is that the MacNeille completion of the type A Bruhat poset is isomorphic as a poset to the set of matrices satisfying the conditions above. So these Hij satisfy all of these conditions. So integer-valued matrices with order relation being just point-wise, entry-wise, less or equal. So, I mean, I've kind of tried to justify to you why this is true, but I'm actually going to prove it to you in a sec. But I think first there's an example. Yes. So let me redo the example of psi3 once more. So now I think of them as, the reason I think of the height functions is I like to think of it in 3 dimensions, right? So literally I want to think of the height, in 3D and have my computer generate those pretty pictures. And so the largest element is actually the lowest height. And you can see, oh yeah, so first, what are the boundary conditions? There are those funny slanted conditions here. So that means there are 2 points that are very low and 2 points that are very high. And so you have this kind of saddle point type shape, which is characteristic of, if you've ever played with any of these models, you always have this type of piecewise linear boundary conditions. And so you're supposed to fill in the inside with some, you have to fill in the inside in some way, and the kind of lowest way you can do it is you decide that you have kind of a folding at the middle here, and you have 2 sides like that. So you're supposed to see here that this is the lowest possibility. And on the contrary, the highest possibility, if you connect, on the contrary, I'm being silly, these 2 points by line, and then there are 2 sloped faces on each side. And then you have all kinds of intermediate possibilities where you can see that you basically see everything on this picture. Like, for example, you see what the covering moves are. The covering moves are you take some local minimum and you make a little bump, and now it becomes a local maximum. And in here you have 2 local minima, and you can turn them into 2 different local maxima. Then you can get both of them at once. Then now you have a new local minimum here and a new one, so you can push them upwards until you've gotten to the top configuration. So I think this is probably the sort of nicest description you can think of as of this poset. OK, so what did I say? Oh yes, I promised to prove the actual propositions, the actual proposition. So again, this is exactly the same proof that they have. I'm just going to draw it slightly differently. And so the idea is extremely simple. You're gonna, you want to show that. So you have one of those height matrices, height functions or whatever, and you want to know that they are part of this poset, basically. And so the way you're going to say that is, well, you know that means if it's in the poset, that means you should be able to express this height function as the supremum of some configurations from the original poset. So you're going to do that completely explicitly. You're going to write this height function as the sub of a bunch of height functions associated to the original poset, so to your permutation matrices in some sense. And the way that Lascoux and Schutzenberger do that, they say so that's the notion of kind of like a base or basis. I'm not sure what the English word is of a poset. They're going to define you don't need every permutation matrix to do that. You only need a subset, which are these bi-Grassmannian permutations. And so you're going to use this kind of subset of permutations, the bi-Grassmannian permutations, to build every height function this way. And so again, I'm giving you a slightly more pictorial version of what are their arguments. So this is supposed to be the same pictures as on the previous slide, except they're a bit flattened because I couldn't be bothered doing in nice 3D. So you should think of this as this is supposed to be a local maximum, basically. And the arrows here are supposed to be the slopes. So when you see a picture like this one, what you really should be thinking in your mind is you have some local little mountain, and then it goes kind of like the gradient is like going, you know, and so there are like ridges, I don't know, like, and you have 4 different regions in which the slope kind of goes downwards in the 4 directions around that maximum. So that's the picture I'm drawing. So the colors encode the local slope, basically. It's a bit of a view of the mind, because of course these are actual integers, and so everything is like discretized, but it's good enough for our purposes. Okay, so now comes the definition. If you consider, well, yeah, I haven't actually told you what the Grassmannian permutation is. So you fix 3 integers I, j, and r with some appropriate inequalities. So I and j are in between 0 and n, and r. Anyway, inequalities so that this picture makes sense. I'm not going to bother going through. And so the actual permutation matrix I drew in black. So these entries are the ones of the bi-Grassmannian permutation. So it starts like the identity, and then at some points it jumps up, then it jumps down, and then it ends just like at the identity matrix. And so the claim is that if you compute the corresponding height function with this little procedure that I gave you, so you're doing partial sums and doing this funny business, I plus j minus 2rij, you'll get exactly this 3D picture when you have exactly one local maximum at the coordinate ij, conveniently. And everywhere else, the idea is that it's really the minimum permutation with this constraint. So if you fix the height to be the height of that, you know, the height at that spot of the bi-Grassmannian permutation, the point is that you try to go downwards as much as you can. So obviously what you're going to do is if you fix, you're kind of trying to, you know, it's like physics, you know, you kind of attach the height function at this point, and then it kind of goes down through gravity everywhere it can. So it kind of slopes down in each direction until it gets to the very bottom configuration, which is this thing, right? So it's kind of, you think of it as a kind of local perturbation of this minimal configuration where you force it to have one local maximum. So yeah, so that's exactly the state mirror. These are exactly the minimal elements, the minimal heights. Oh, I always get confused with this is minimal versus maximal. Yeah, I think it's correct as written. Yes.
That's the least volume you can have in
yeah, that's right.
Keep it the blue spot.
Yeah, let's trust the slides, not me. So there are the minimal elements such that the height is fixed at some point to be essentially any value you like, any value with parity constraints. So it's I plus j minus 2r. And so now the proof of the proposition becomes trivial, because you say, well, take any height matrix that satisfies all the inequalities we had before, then you can check explicitly that it's just the supremum of all of these ones where you fixed at each point the height to be the one you want, basically. So it's very easy. You're saying, I want the height to be fixed everywhere. I'm just going to, you know, go over all the ij's, and each time I'm going to use the corresponding bi-Grassmannian permutation, and that's by definition is going to give you, you know, the height function you want. So it's kind of a completely logical proof, but it's nice. You know, if you think about it in detail, yeah, it's a clever proof.
Sorry, but
not mine.
Sorry, but for every fixed ij, you still have this free parameter r, right?
That's right. So r is going to fix the actual height, right? So there are 3 parameters: the location at which you want to fix the height and the actual value of the height. So these are the 3 parameters. So here it's fixed explicitly. So again, there's because R is related to, there's this stupid redefinition which makes all my formulas look ugly. So this is the same formula that says that hij equals I plus j minus 2R or whatever. So up to some trivial redefinition, these three parameters are exactly the location and the value of the height at a given point. And that's it. Then you check that all these inequalities are stable by, I already said that, stable by sub, so that concludes the further proposition. So that's nice and clean. OK, a few more words about type A. As I said, I'm going to get to my first open question, a very trivial one, but something I've never understood. So let's go through that. So as I said, you can see everything on this poset just staring at those pictures. So in particular, you know what the covering moves are, which means you realize immediately, in particular, this is a graded or ranked poset, depending on your favorite terminology. So that's clearly like a ranking here, 0, 1, 2, 3, 4. And so you can make this completely explicit. The ranking function, or the grading, if you like, of your poset is simply the volume, as mentioned earlier. So the volume under the surface, you can think of it as your ranking. So because I have parity things, you should probably divide by 2. But essentially, it's just the sum of all the heights at every point, up to a factor of 2. And then yes, and then let me say that x, well, a covering relation then is exactly an inequality with the fact that y is x plus 1. So yeah, so that's the proposition basically. The covering, so these are the covering relations because it's a rank poset in other words, and very explicitly, the covering relations are exactly what I said earlier. You basically take a local. I'm getting really confused about minima versus maximum. You take a local minimum. Was that? Yeah. Sorry, I'm very not thinking straight today. Anyway, so yes, you take a local minimum, you bump it to make it into a local maximum, and you're happy. All right. So super easy. So before I get to my open question, I probably should say a word about alternating sign matrices. After all, they were already in the previous talk. So yes, these are all alternating sign matrices in disguise. Fine. So the way you can think about it is, I define for you a rank matrix out of a permutation matrix, and then I did this operation of taking the supremum, or infimum of the ranks, or supremum of the height functions. So you can do the inverse transformation, starting from a rank matrix or height matrix. You can revert the process, reverse engineer and say what would be the permutation matrix associated to that rank matrix, and you get this simple equation, which is like, instead of integrating once in each direction, you're kind of differentiating once in each direction. But of course, now you can do that process even for rank matrices which do not come from permutation matrices, like this new extra one we introduced in the middle. So yeah, so in this slide, I went back to rank matrices, not height matrices, whatever. Anyway, so you have all of these rank matrices, you do the inverse process, and sure enough, you get back to all the permutation matrices you started from, but then you also get this extra one, which is this alternating sign matrix we saw earlier. So that's the general theorem that they're in bijection. So no big surprise there. Yes, so there's a connection to the ASM story as well. So applying this transformation to all of W results in a set of ASMs. This is, again, mentioned in the paper of Lascoux and Schutzenberger as a little footnote. They don't really say much about that, which are precisely those matrices we've seen already yesterday and today. So I'm not going to go through the definition again. Now, what's kind of curious to me is that ASMs were actually introduced much earlier in a completely unrelated work of Mills, Robbins, and Rumsey about lambda determinants. And I don't really know why this, what's the connection between lambda determinants and MacNeille completions? Maybe there is a connection that some people in the audience are aware of, but for me it seems to be completely unrelated. So there's something kind of interesting. And yes, so the number of ASMs is known. So in particular, the cardinality of the MacNeille completion in type A is given by the famous sequence, which is the number of ASMs. And my interest in this subject is, of course, due to the fact that these configurations, as again mentioned earlier, are in bijection. So these ASMs are in bijection with configurations of the 6-vertex model with domain world boundary conditions. And in fact, the height function representation I used earlier is the one we traditionally use in the 6-vertex model, so that's why I used it. So here's the connection to kind of solvable lattice models. So here finally comes my open question. So in particular, using quantum integrability, you can compute not only the enumeration, but actually the weighted enumeration. So you can give a weight to, well, you have 6 configurations. You can probably compute separately, you can, the enumeration where you fix the number of zeros of this type, zeros of that type, and also ones and minus ones. So it's not, So it's not that interesting maybe to distinguish between those 2 types of zeros, but in particular what's interesting is you can do an enumeration where you count the number of minus ones in the ASM. So that can be done, and people have done that. There are plenty of formulas. I may have played that game at some point in some of my papers. But really, from the point of view of poset theory, none of these quantities are particularly relevant. I mean, the number of minus ones, what do they even mean anyway, in terms of MacNeille completion? So a much more natural quantity would be the graded enumeration, where you say you sum over all elements of the MacNeille completion, and the exponent of your formal variable would be the ranking. And I actually don't know how to compute that. So this is an elementary question for all of you.
This is going to be Algebraic polynomial.
Yes, that is true. Yes, we can state that as a theorem. Yes. But that's not quite good enough. I want the actual answer, not just. But yeah, that's true. Yes. Now, what's funny is that actually there is a special case that is known. As I said, you can do some enumeration where you also keep track of the number of minus ones. So if you combine these 2 things in a very specific way, you do the so-called 2 enumeration, which is known to be simpler than the 1 enumeration. Then the answer turns out to be known. This is this connection with the lambda determinants. In this case, the partition function turns out to be, so this Z here, turns out to be a Vandermonde lambda determinant, and there is a Vandermonde formula for lambda determinants of Vandermonde matrices. And so in this case, you know the explicit answer. So I only know if I introduce this extra annoying 2 to the power of the number of minus ones, but I don't know anything else about this graded enumeration.
Oh, so the statistics, if you write it in terms of the 6-vertex model?
Yes.
What is it?
Exercise, figure it out. Yes, that's the correct question to ask. Yes.
But the grading is exactly 6-vertex model height function, so you've just marked the total height.
Don't try to solve it now. Don't spoil the whole thing. Please wait till the end of the talk to solve the problem.
Yeah.
All right. OK, so the second thing I want to talk about is the type B poset. OK, so you play the same game, but now instead of taking the group G to be GLN, you can take either the symplectic group or the odd orthogonal group. You may wonder why I'm not talking about the even orthogonal group. You can try, but I've failed to find anything interesting in that case. So in other words, yeah. So remember that when I say type B, it's type B or type. So the Weyl group of type B or type C is the same, and the corresponding posets are the same. So you can make a choice which one. I call it type B because, well, it's the letter that comes before C, but it's either B or C. SO2n would be type D, and that one I don't know what to do about. So you can start playing around, and then quickly you realize the simplest way to think about it is just as a subposet of the type A GL2n. So in other words, you could do the same game, play the same game using like the Bruhat decomposition. You could do all of that, and that would work just fine. But really, if you want to go straight to the combinatorial core of the problem, you might as well just think of it in terms of type A. And so the way you do this is you say consider all permutations which are palindromes. So again, I'm pretty sure that was also in the Lascoux and Schutzenberger paper. So the way the definition is simply that it's a permutation of of size 2n, even size, in such a way that if you sum the opposite entries, like 4 plus 1, 3 plus 2, you always get the same number, which is always 2n plus 1. Yes. So you can check that for all of these, 1 plus 4, 3 plus 2, you always get 5. And so you get a new poset. So it is new in the sense that some of these errors weren't there before. They're not. So the covering relations look different, but it's just a subposet. So I've given to you the first non-trivial example, which is n equals 2. Which has 8 elements. That seems right. And the one thing to observe is that immediately you're going to run into the same type of problems we had for type A, which is some of these errors are crossing, and it's very, tempting to put an extra element where the errors are crossing, right? And I'm going to do that. And so yeah, maybe I should say a few words about. So in the theory of ASMs, that Kupperberg wrote his original paper about enumerating ASMs using the 6-vertex model, but then he wrote a sequel, which is very interesting, which has lots of interesting stuff in there, which is symmetry classes of alternating sign matrices under one roof, or some such title, I forget. And so in this paper, he investigated all kinds of subsets of alternating sign matrices which have extra symmetries. So here's, for example, one class that he definitely considered. Is probably the easiest class after the whole set of ASMs. It's the half-tone symmetric alternating sign matrices. So, so here I've drawn for you all of 8 of them, and of course I'm going to argue that it has something to do with the previous picture. But for now, let's just take that as a definition. Take all the 4x4 alternating sign matrices which are invariant under 180-degree rotation, and so there are 8 of them. Oh, really? Oh, sorry, you're right. There are 10 of them. Thank you. I'm glad to see people are following carefully all the mistakes that I'm saying. Yes, absolutely. So there are 8 permutation matrices and 2 extra alternating sign matrices. And there's an obvious order relation on them. And if you define it, you find, surprise, it's a poset that looks very much like this one, but completed. And it's true. In the example of n equals 2, this is indeed the MacNeille completion, and so it's in bijection with the half-tone symmetric alternating sign matrices. And so this is kind of like where, yeah. So this is the only not trivial thing that I'm going to say today. Is this is not true. Of course, that if I'm saying it's an obvious guess, that means it's probably not true. So the only theorem I want to formulate today is fix that little discussion about type B. So the first thing is, yeah, the number of half-tone symmetric ASMs is well known, due in particular to the work of Kupperberg. You can find it in the OEIS as 1, 10, 1, 2, 10, 140, 5, 5, 44, etc. And if you compute the cardinality of the poset of type B, you can just do that by hand. I literally originally did it by brute force. You can run an algorithm that produces, not very efficiently, the MacNeille completion of any poset. And you get those numbers. And obviously, the mismatch happens pretty quickly, actually. Even for n equals 3 already, these numbers do not match. And they're always smaller, suggesting that maybe we went a little bit overboard with all of the half-tone symmetric ASMs, which is the case. And the subtlety lies in, yeah, there's one proof in this original paper which has a gap, and that gap actually was crucial because it's exactly the difference between these two numbers. So we're going to go through that in the last part of the talk. How much time do I have? OK, great. So first, what is the proposition? Oh, I very optimistically wrote this as 2023, even though it's not published. But anyway. Yes, so anyway, proposition in 23 plus or minus 20 years, to be conservative. So in type B, W tilde, so the MacNeille completion of type B Bruhat poset is actually isomorphic to the set of HTS ASMs, such that for any centered rectangle, so you take any sub-rectangle in your half-tone symmetric ASM, the sum of entries is actually non-negative. Okay, so the explicit expression is given here. So that's this weird constraint in the middle. So of course this looks very cryptic. That's because ASMs are probably not the right way to think about it. It's better to think in terms of height functions. So I'm going to give you the height function version, height matrix version in a second. But that's the theorem. Well, actually, I formulated it as a proposition. I don't think it deserves being called a theorem. But anyway, yeah. So in terms of height functions, this inequality is actually very simple. That's what it says. So these are exactly the same height functions we had in type A. So it had like fixed boundary conditions, which are the same. It has this kind of one Lipschitz condition that means neighboring values differ by plus or minus 1. It has the obvious symmetry you would expect from the fact that it's half-tone symmetric. So Hij equals Hn minus I n minus j, where capital N is just 2 small n. So it's just because we doubled the size in some sense. And the only non-trivial constraint, which is not the one you would expect for half-tone symmetric ASMs, is that if you change the only one of the two entries and you flip it, then you have this inequality between the two. So that's a very interesting non-local constraint between the height functions at 2 points which are related not by half-tone symmetry, but rather by mirror symmetry under one of the axes, vertical or horizontal axes. So as usual, all these inequalities are obviously satisfied by height matrices of palindromes. They're stable by taking sub. So as in type A, all you need to do is to find minimal elements associated to every possible value of the height function that satisfies those inequalities. So that's the crucial lemma that is. So if you look at the paper of Lascoux and Schutzenberger, they only considered 2 out of these 4 cases. And they're not the interesting ones. So there's only one interesting case, I'm going to argue in a sec, which is this one. I think they only did these 2 cases. And if you don't have this one, then you miss that inequality, which is this one, which is the crucial one. So let's go through the arguments. So you fix a point ij, which is always represented as a blue dot. But now, of course, it has images, right? So first, it has a half-tone symmetric image, which is here. But also, I care about the flips under horizontal and vertical lines. So you have those red dots. So I fix a blue dot and all its images, and I fix the height function at that point, and I want to find the minimal height function that satisfies all these constraints of inequalities. It's a very elementary exercise, but it does have to be divided into a bunch of cases. So the easiest case would be, for example, if I and j are in this quadrant, and the height is not too big or something like that, and then you find basically 2 local little mountains, just like the type A, but rotated 180 degrees and duplicated. So this is the super easy case. And there are 2 more easy cases. They look a bit messy, but they're really not much harder, where if the blue dot is here, the blue dot is here, yeah, the 2 mountains tend to kind of get a little bit mixed up together, but they still kind of only 2 local maxima. So it's really just the same story. It's the the half-tone symmetric version of the type A. So, and same here. You have blue here. So it's still different. If you think about the corresponding permutation, they all look a little bit different. The combinatorics is different, but ultimately you only have 2 local maxima, which is always those points where you have all those colors all around. But then this case is more interesting. If you do the analysis without this extra condition, you can do it. You'll find a local maximum, like a minimum configuration, and that configuration will not correspond to a permutation. It will correspond to a half-tone symmetric ASM, but it's just not in the poset. So you're not allowed to do that. So then you backtrack and you say, oh, I did something wrong. Oh, yeah, I violated this inequality. So now you impose the extra condition that this red dot also has a fixed value of the height. So you have now 4 different peaks. Thank you. Slide. And now you do the same problem. So now it's a bit more complicated, but you have 4 mountains, and they nicely can interact in some way. And that is a valid permutation, the height function of a permutation matrix. And then the proof is the same. You say now any height function is the supremum over all ij's and all heights of one of these elements, depending on the 4 configurations. So that's the crucial lemma. OK, so now the open questions. The obvious one, what is the closed formula for the cardinality? This is the one that I've been stuck on for several years now, and I really like to know the answer, but I don't. So hopefully one of you can tell me. You can, of course, do all the variations you do in type A. You can do the graded enumeration. I've even less clue how to do that. Or you could try to say, well, maybe I should do the 2 enumeration, because we know the 2 enumeration of half-tone symmetric ASMs is, well, again, easier than the 1 enumeration. So maybe this is an easier object to consider, either graded or ungraded for all I know. I mean, it's not like you don't need to have this extra variable t. The ranking function being, again, I haven't defined it, but it's again the kind of the total height, basically. Maybe now you divide by 4 because you have all those symmetries or something, but it's the same story. And the final question is about asymptotics. So this is the only one where I'm ready to at least give a conjecture. So since we have exact enumeration of half-tone symmetric ASMs, we know in particular their asymptotic number. It grows like n squared. The logarithm grows like n squared, as always in lattice models. And my weak attempt as a conjecture would be that actually this extra height constraint doesn't really affect the asymptotic behavior. So hopefully this is true, that the log should be asymptotically the same as the number of half-tone symmetric ASMs. But even that is, this is just a conjecture, really. And I think this is all.